A few years ago, many people thought particle physics was almost finished. Scientists had discovered the Higgs boson. The standard model seemed complete. And while there were still unanswered questions, it felt like humanity was finally putting together the last pieces of the puzzle. Then CERN started collecting more data, and something unexpected happened. The deeper physicists looked into the universe, the less complete the picture became. New measurements began exposing cracks in theories that had survived for decades. Strange particles kept appearing in places nobody expected. Some long-promised discoveries refused to show up at all. And with every collision inside the Large Hadron Collider, scientists found themselves facing an uncomfortable possibility. What if our best understanding of reality is missing something fundamental? Now, before we go any further, CERN has not discovered a machine that can destroy Earth. They have not opened a portal to another dimension, and they have not created a black hole that will swallow the planet. The real story is far more interesting. The frightening part isn't that CERN found something dangerous. It's that after decades of research, trillions of particle collisions, and one of the most sophisticated scientific instruments ever built, physicists are being forced to admit how much they still don't know. Some of the universe's biggest mysteries, dark matter, dark energy, gravity, and even the reason anything exists at all, remain unsolved. And the latest discoveries suggest those mysteries may be even deeper than anyone imagined, because CERN's most unsettling finding may not be a new particle. It may be the realization that we're still looking at only a tiny fraction of reality, and what lies beyond that fraction could completely change our understanding of the universe. If you only follow CERN through social media headlines, you could be forgiven for thinking something terrifying has already happened. Every few months, a new wave of articles appears claiming that scientists have discovered evidence of another universe, broken the laws of physics, created miniature black holes, or found something that could change reality itself. The language is dramatic because dramatic headlines get attention, but those headlines often miss what is actually happening. The truth is both less sensational and far more important. CERN's recent discoveries are not frightening because they reveal some immediate danger. They are frightening because they reveal how incomplete our understanding of the universe may be. For decades, physicists have relied on a framework called the standard model. It is one of the most successful scientific theories ever created. It describes the fundamental particles that make up matter and explains how most of the known forces of nature operate. Its predictions have been tested countless times and repeatedly confirmed with extraordinary precision. For a long time, many scientists expected that larger experiments would simply fill in a few remaining details. Instead, the opposite seems to be happening. The more precisely researchers measure nature, the more they encounter mysteries that the standard model cannot explain. Consider dark matter. Every observation of galaxies suggests that enormous amounts of invisible matter exist throughout the universe. Without it, galaxies should fly apart. Yet despite decades of searching, nobody knows what dark matter actually is. Then there is dark energy, the mysterious phenomenon causing the expansion of the universe to accelerate. It appears to make up most of the cosmos, yet scientists still do not know its true nature. Gravity presents another problem. It governs the motion of planets, stars, and galaxies, but it refuses to fit neatly into the same framework that explains the other fundamental forces. Even more puzzling is the existence of matter itself. According to our best understanding of the Big Bang, matter and antimatter should have been created in nearly equal amounts. When matter and antimatter meet, they annihilate each other. If the early universe contained equal quantities of both, almost everything should have vanished. Clearly that did not happen. Stars exist, galaxies exist, planets exist, we exist. Somewhere in the history of the universe, a tiny imbalance emerged that favoured matter over antimatter. Without that imbalance, there would be no atoms, no chemistry, and no life. Scientists know the imbalance occurred. What they do not know is why. This is where CERN enters the story. The Large Hadron Collider was built partly to answer questions like these. By accelerating particles to extraordinary speeds and smashing them together, scientists can recreate conditions similar to those that existed shortly after the Big Bang. These collisions generate enormous amounts of data, allowing researchers to study nature at its most fundamental level. What makes recent results so interesting is that they are not simply confirming existing theories. In many cases, they are exposing gaps. Some expected particles have failed to appear. Certain measurements continue to challenge theoretical predictions. New particle combinations are being observed in greater detail than ever before, and every improvement in experimental precision seems to uncover additional layers of complexity. That creates a strange situation. Physics is not in crisis because experiments are failing. Physics is in crisis because experiments are succeeding. The machines work, the detectors work, the measurements are becoming more accurate every year. Yet the answers scientists hoped to find are not appearing where they expected them. Imagine completing a massive puzzle and realizing that half the pieces belong to a different picture. That is increasingly how modern particle physics feels. Researchers possess an incredibly successful theory, but they also possess overwhelming evidence that the theory cannot be the final story. And that may be CERN's most significant discovery so far. Not a single particle, not a single experiment, but the growing realization that the universe is still hiding something fundamental, something powerful enough to shape galaxies, influence cosmic evolution, determine why matter exists, and perhaps reveal entirely new layers of reality. The unsettling part is that nobody yet knows what that missing piece looks like. They only know that it is there. To understand why CERN's discoveries matter, you first need to understand what scientists are actually trying to do there. Because despite all the headlines about particle collisions, exotic matter, and billion-dollar experiments, the goal is surprisingly simple. CERN is trying to answer one question. What is reality made of? Humans have been asking that question for thousands of years. Ancient civilizations wondered whether everything was made from earth, air, fire, and water. Later, scientists discovered atoms and believed they had finally found the fundamental building blocks of nature. Then atoms turned out not to be fundamental at all. Inside atoms were electrons orbiting a nucleus. Inside the nucleus were protons and neutrons. Then protons and neutrons themselves were found to contain even smaller particles called quarks. Every time scientists thought they had reached the bottom layer of reality, another layer appeared underneath. By the 20th century, physicists realized they needed a way to look deeper than ever before. Ordinary microscopes were useless. Even the most powerful optical instruments could not reveal objects that small. Nature offered only one solution. If you want to see smaller structures, you need higher energies. A simple comparison helps explain why. Imagine trying to examine a grain of sand from several kilometers away. You would not see much detail. Move closer, and more features become visible. Move even closer, and you begin seeing tiny imperfections on the surface. Particle physics works in a similar way. Higher energies allow scientists to probe smaller and smaller scales. That is why particle accelerators were invented. These machines accelerate particles to enormous speeds before smashing them together. The collision acts like a microscopic explosion, briefly revealing the ingredients hidden inside matter. The Large Hadron Collider, or LHC, is the most powerful machine ever built for this purpose. Located beneath the border between France and Switzerland, the accelerator forms a circular tunnel roughly 27 kilometers in circumference. Inside that tunnel, powerful superconducting magnets guide beams of particles around the ring thousands of times every second. The particles usually being accelerated are protons. As the protons race around the collider, they approach speeds incredibly close to the speed of light. Eventually, two beams travelling in opposite directions are directed toward one another. Then they collide. When people hear the word collision, they often imagine two objects simply crashing together. What actually happens is much more dramatic. The energy concentrated into a single proton collision can briefly recreate conditions that have not naturally existed since the earliest moments of the universe. Temperatures become far hotter than the centre of the sun. Energy transforms into matter. New particles appear and disappear almost instantly. Most of these particles survive for only tiny fractions of a second. Scientists never observe them directly. Instead, enormous detectors surrounding the collision points record the debris left behind. Computers then reconstruct what happened by analysing millions of tracks, energy signatures, and decay patterns. It is similar to investigating a car crash by examining scattered pieces across a highway. The collision itself is over immediately. The challenge is figuring out what happened from the evidence that remains. This is why CERN generates such staggering amounts of data. Every second, millions of collisions occur. Most are ordinary and predictable. Hidden among them are the rare events physicists desperately want to study. Finding those events is like searching for a single specific grain of sand on a beach. Yet that effort has produced some of the biggest discoveries in modern science. The most famous example came in 2012 with the discovery of the Higgs boson. For decades, physicists believed the Higgs particle must exist because their equations required it. The LHCb finally found evidence confirming that prediction, completing one of the most important chapters in particle physics. Many people assumed that discovery would be the beginning of a new era filled with revolutionary findings. In some ways it was, but not in the way scientists expected. Researchers hoped the Higgs would point directly toward new physics. They expected clues about dark matter, hidden dimensions, supersymmetry, or entirely new particles waiting beyond the standard model. Instead, the Higgs largely behaved exactly as existing theories predicted. That was both a triumph and a problem. The theory worked, yet the universe's biggest mysteries remained unsolved. So CERN continued pushing forward, collecting more data, improving detectors, and increasing precision. Because the mission was never simply to discover one particle. The mission is to understand why the universe exists in its current form, why matter has mass, why forces behave the way they do, why the cosmos contains structures like stars and galaxies, and perhaps most importantly, whether the particles we know today are truly the deepest layer of reality or merely the latest layer humanity has managed to uncover. That question drives every collision inside the Large Hadron Collider, and so far nature has shown no sign of running out of surprises. Before we talk about the problems physicists are facing today, it's important to understand just how successful the standard model has been. Because when scientists say the standard model might be incomplete, they are not talking about a theory that failed. They are talking about one of the most accurate scientific frameworks ever created. In fact, many physicists consider it one of humanity's greatest intellectual achievements. At its core, the standard model is an attempt to answer a deceptively simple question. What is everything made of? The answer begins with a surprisingly small collection of particles. Everything you can see around you, your body, the air, the ground, the oceans, the stars, is built from a handful of fundamental ingredients. The first group is called quarks. There are 6 types or flavours of quarks: up, down, charm, strange, top and bottom. In everyday life, only 2 of them matter very much: up quarks and down quarks. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up quark. Since atoms are built from protons and neutrons, most visible matter ultimately comes from combinations of these tiny particles. Then there are leptons. The most familiar lepton is the electron. Electrons orbit atomic nuclei and are responsible for chemistry, electricity, and countless processes that make life possible. Leptons also include particles called neutrinos. These are among the strangest objects in nature. Trillions of them pass through your body every second, yet you never notice because they interact so weakly with matter. Together, quarks and leptons form the basic building blocks of the universe, but particles alone are not enough. The universe also needs forces. Without forces, particles would simply drift through space without interacting. The Standard Model explains 3 of the 4 known fundamental forces. The first is electromagnetism, which governs electricity, magnetism, light, and atomic structure. The second is the strong nuclear force, which binds quarks together and holds atomic nuclei intact. Without it, protons and neutrons would instantly fall apart. The third is the weak nuclear force, responsible for certain types of radioactive decay and crucial processes inside stars. Each force is carried by its own messenger particles. Photons carry electromagnetism. Gluons carry the strong force. The W and Z bosons carry the weak force. For decades, scientists developed increasingly sophisticated equations describing how all these particles interact. What made the theory remarkable was not just its ability to explain known observations, it also predicted discoveries before they happened. Again and again, the equations pointed toward particles that had never been observed, and again, experiments eventually found them. This predictive power gave physicists enormous confidence. Imagine writing down equations today that predict the existence of a completely unknown particle. Then 20 years later, someone builds a machine powerful enough to test the prediction and discovers exactly what your calculations described. That happened multiple times throughout the development of the Standard Model. Few scientific theories have ever demonstrated that level of accuracy, yet one prediction stood above all the others: the Higgs boson. By the 1960s, physicists had a problem. Their equations suggested fundamental particles should have no mass at all. Clearly that couldn't be right. Everything around us has mass. Something was missing. Several researchers proposed a solution involving an invisible field that fills all of space. As particles move through this field, they acquire mass. The stronger their interaction with the field, the heavier they become. If this idea was correct, there had to be a particle associated with the field. The particle became known as the Higgs boson. The problem was that nobody could find it. For decades, the Higgs remained one of the most famous missing pieces in physics. Entire generations of scientists searched for evidence. Then in 2012, the Large Hadron Collider finally detected a particle matching the predicted properties of the Higgs boson. The discovery made headlines around the world. It wasn't just the discovery of a new particle. It was confirmation that a theory developed over decades was fundamentally correct. At that moment, the Standard Model appeared stronger than ever. Every major particle predicted by the theory had been found. Every major force described by the theory had been observed. Many of its calculations matched experimental results to astonishing precision. If physics were a criminal investigation, the Standard Model looked like a case that had been solved, but there was a problem hiding beneath that success. Even at the moments of its greatest triumph, physicists knew the theory was incomplete. The Standard Model explains the particles we can observe. It explains most interactions we can measure, but it leaves some of the biggest questions in science completely unanswered. It says nothing about dark matter. It cannot explain dark energy. It does not successfully incorporate gravity, and it offers no convincing explanation for why the universe contains vastly more matter than antimatter. In other words, the Standard Model may describe the visible universe with extraordinary precision, but the visible universe appears to be only a small fraction of everything that actually exists. That realization has become one of the defining challenges of modern physics, because if the most successful theory ever created cannot explain most of reality, then something important is still missing. For most of scientific history, success usually meant fewer mysteries. You discover a law of nature, explain a phenomenon, and reduce the number of unanswered questions. Modern particle physics has taken a very different path. The standard model became more successful with every experiment. Its predictions kept matching reality. New particles were discovered exactly where the theory said they should be. Precision measurements repeatedly confirmed its accuracy. Yet instead of making the universe seem simpler, this success exposed a deeper problem. The theory works almost too well, and that has become frustrating for physicists. The reason is simple. Scientists know with absolute certainty that the standard model cannot be the final description of reality. Not because it is inaccurate, because it leaves enormous parts of the universe completely unexplained. The most obvious example is dark matter. When astronomers observe galaxies, they find something strange. The stars orbit much faster than they should. Imagine spinning a ball attached to a string. If the ball moves too fast, the string eventually breaks because there isn't enough force holding it in place. A similar principle applies to galaxies. Based on the amount of visible matter present, galaxies should not have enough gravity to remain intact. The outer stars should escape into space, but they don't. Something invisible is providing extra gravity. This hidden substance appears to surround galaxies and galaxy clusters across the universe. Scientists call it dark matter. The evidence is overwhelming. The problem is that nobody knows what it is, and the standard model offers no particle capable of explaining it. Think about that for a moment. Physicists have built an incredibly successful theory describing fundamental matter, yet that theory cannot explain a substance that appears to outweigh ordinary matter several times over. That alone would be a major problem, but it gets worse. In 1998, astronomers made another shocking discovery. The expansion of the universe is accelerating. Most scientists expected gravity to gradually slow cosmic expansion over time. Instead, distant galaxies were moving away from one another, faster and faster. Something appeared to be pushing the universe apart. That unknown phenomenon became known as dark energy. Today, observations suggest dark energy makes up the majority of the universe's total energy content. And once again, the standard model has no explanation for it. This creates a strange situation. Everything humans can directly see, stars, planets, gas clouds, black holes, galaxies and people, appears to represent only a small fraction of the cosmos. The vast majority consists of dark matter and dark energy, yet our most successful theory describes neither. Imagine a marine biologist studying Earth's oceans while only understanding 5% of the water. That is roughly where modern physics finds itself. Then there is gravity. At first this may seem surprising. After all, gravity is one of the oldest forces studied by science. Isaac Newton described it centuries ago. Albert Einstein revolutionized our understanding of it in the early 20th century. So why is gravity still a problem? Because it refuses to fit into the same mathematical framework as the other fundamental forces. The standard model successfully combines electromagnetism, the weak force, and the strong force into a unified quantum description. Gravity remains the outsider. Whenever physicists attempt to merge gravity with quantum mechanics, the mathematics becomes problematic. The two greatest scientific achievements of the 20th century work beautifully on their own, but together they refuse to cooperate. Then comes perhaps the most unsettling mystery of all. Why does anything exist? This isn't a philosophical question, it's a physics question. According to current theories, the Big Bang should have produced nearly equal amounts of matter and antimatter. Matter and antimatter are like opposites. When they meet, they destroy each other and release energy. If equal amounts existed in the early universe, mutual annihilation should have eliminated almost everything. The result would have been a universe filled with radiation and very little matter. No stars, no planets, no life. Yet clearly, matter survived. Some tiny imbalance favoured matter over antimatter. Without that imbalance, none of us would be here. Scientists have identified certain processes that create slight differences between matter and antimatter, but the known effects appear far too small to explain the enormous imbalance we observe today. Something else may have happened, something not included in the standard model. This is why many physicists believe new physics must exist beyond our current theories. The evidence is everywhere. Dark matter points toward it. Dark energy points toward it. Gravity points toward it. The existence of matter itself points toward it. And yet every time scientists search for the missing pieces, nature remains frustratingly silent. No obvious new particles, no dramatic breakthroughs, no clear roadmap, just a growing list of mysteries surrounding a theory that is simultaneously brilliant and incomplete. That tension defines modern particle physics. Researchers possess one of the most successful scientific models ever created, but they also know that model cannot explain some of the most important features of reality. And that realization has transformed CERN's mission. The goal is no longer simply to confirm what we already know. The goal is to find the missing pieces hiding beyond the edge of our current understanding. If CERN hopes to find the missing pieces of physics, the strategy is straightforward. Collect more data, then collect even more. That idea may sound simple, but in particle physics, data is everything. Many of the phenomena scientists are searching for are incredibly rare. A new particle might appear only once in billions or even trillions of collisions. A subtle deviation from theoretical predictions might be hidden inside a tiny statistical effect. Discovering something new often depends less on increasing energy and more on accumulating enormous amounts of information. This is why CERN's current era, known as Run 3, has attracted so much attention. To understand its importance, we need to go back briefly. The Large Hadron Collider first began operating in 2008. Over the following years, it completed multiple runs, each producing larger data sets and more sophisticated measurements. Run 1 delivered the discovery of the Higgs boson in 2012, one of the biggest achievements in modern science. Run 2 expanded the search for new particles and explored the Higgs in greater detail. Then CERN temporarily shut down the collider for a major upgrade program. For several years, engineers and scientists worked underground, replacing components, improving detectors, upgrading electronics, and preparing the machine for its next phase. When Run 3 officially began, it wasn't simply the old collider restarting. It was a more capable version of the LHC. The upgraded machine could operate with higher efficiency, produce more collisions, and generate larger data sets than ever before. That matters because every collision is effectively an experiment. Each one offers another opportunity to glimpse something unexpected. Imagine trying to detect a rare species of animal hidden somewhere in a vast forest. If you spend one day searching, your chances are low. Spend a year searching, and your chances improve dramatically. Particle physicists face a similar challenge. The rarest events require enormous sample sizes before they become visible. Run 3 is providing exactly that. The scale of data collection is difficult to comprehend. Every second, detectors record information from countless particle interactions. The raw data generated is so large that sophisticated filtering systems must immediately decide which events are worth saving and which can be discarded. Even after filtering, researchers are left with massive datasets requiring advanced computing systems to analyse. And this is where things become interesting. Most people imagine discoveries occurring when scientists suddenly observe a completely new particle appearing on a computer screen. In reality, many breakthroughs emerge gradually. Researchers analyse years of data. Patterns begin to appear. An unexpected excess shows up in a graph. A measurement consistently differs from theoretical expectations. A rare decay occurs slightly more often than predicted. At first, these signals may seem insignificant. Then additional data arrives. The statistical confidence grows. Eventually, what looked like a random fluctuation may turn into evidence of something real. That process depends entirely on having enough data. The more collisions scientists collect, the more precisely they can test the standard model. And precision is becoming one of the most powerful tools in modern physics. Earlier generations of particle accelerators focused largely on finding missing particles. Today's physicists are increasingly interested in finding tiny imperfections. A discrepancy of just a few percent might point toward entirely new laws of nature. A subtle anomaly could reveal the influence of unknown particles that cannot be observed directly. This is one reason Run 3 is so valuable. The improved detectors are not merely collecting larger quantities of information, they are collecting better information. Events can be reconstructed with greater accuracy. Particle tracks can be measured more precisely. Rare processes can be isolated more effectively. As a result, physicists can examine nature in unprecedented detail. And sometimes the most important discoveries emerge not from dramatic surprises, but from increasingly precise measurements. The challenge is that greater precision often creates greater confusion. Instead of solving mysteries, it can reveal new ones. A result that once appeared consistent with theory may begin showing small but persistent tensions. An expected explanation may become less convincing as better data arrives. Questions that seem settled can suddenly reopen. That's exactly what many researchers hope will happen during Run 3. Not because they want existing theories to fail, but because science advances most rapidly when observations force new ideas. If every measurement perfectly matches expectations, progress becomes difficult. If reality starts deviating from predictions, entirely new possibilities emerge. That is why the current phase of CERN's research feels so important. The collider is operating at extraordinary performance levels. The detectors are more powerful than ever. The data sets continue to grow, and somewhere inside those trillions of collisions could be the clue physicists have been searching for. A hint of dark matter, evidence of an unknown force, or the first sign that the standard model is only part of a much larger picture. For now, the data keeps pouring in, and with every new collision, the chances of finding something unexpected continue to grow. When most people hear the word particle, they imagine something simple, a tiny object, a basic building block, something indivisible. But the deeper physicists have looked into matter, the stranger particles have become. One of the most surprising developments at CERN over the last several years has not been the discovery of an entirely new fundamental particle. Instead, it has been the appearance of increasingly exotic combinations of particles that challenge our understanding of how matter organises itself. At first glance, this might sound like a minor technical detail. In reality, it has become one of the most active areas of research in particle physics. To understand why, we need to start with quarks. As we discussed earlier, quarks are among the fundamental building blocks described by the standard model. They rarely exist alone. The strong nuclear force binds them together into larger structures known as hadrons. The most familiar hadrons are protons and neutrons. A proton contains 3 quarks. A neutron contains 3 quarks. For decades, physicists assumed that nature largely preferred simple arrangements like these. There were theoretical reasons to suspect more complicated combinations might exist, but they were often viewed as unusual possibilities, rather than major components of particle physics. Then experiments began finding them, as detectors became more powerful and datasets grew larger. Researchers started observing particles that did not fit neatly into the traditional picture. Some appeared to contain 4 quarks, others seemed to contain 5. These became known as tetraquarks and pentaquarks. At first, many scientists were cautious. Extraordinary claims require extraordinary evidence, and particle physics has a long history of apparent discoveries disappearing when additional data arrives. But over time, the evidence became stronger. More observations followed. More candidates appeared. The pattern became difficult to ignore. Nature seemed perfectly willing to create structures far more complicated than physicists once expected. The Large Hadron Collider has played a major role in these discoveries. Its enormous collision energies produce vast numbers of heavy particles that rarely occur elsewhere. Many decay almost immediately, but their decay products leave fingerprints that detectors can reconstruct. By carefully analysing those fingerprints, researchers can identify entirely new particle states. Some of these states exist for only tiny fractions of a second, yet even those brief appearances can reveal important information about the forces governing matter. What's particularly interesting is that many exotic particles contain heavy quarks, such as charm quarks or bottom quarks. These heavier relatives of the familiar up and down quarks behave in ways that help physicists test the limits of existing theories. In some cases, researchers are still debating the true nature of what they are observing. Are these objects tightly bound collections of 4 or 5 quarks? Are they more like molecular structures formed from smaller particles interacting with one another? Or are they something entirely different? The answer remains unclear. And that uncertainty is exactly what makes them valuable. Particle physics advances whenever scientists encounter systems that they do not fully understand. The exotic particles emerging from CERN provide new laboratories for studying the strong force, the most powerful force in nature. Ironically, it is also one of the least intuitive. The strong force behaves very differently from gravity or electromagnetism. Instead of weakening as particles move farther apart, certain aspects of the strong force become stronger. This unusual behaviour traps quarks inside larger particles and prevents them from existing freely under normal conditions. As a result, understanding how quarks combine remains an ongoing challenge. Every newly observed particle state provides another clue. Every exotic configuration helps researchers test their mathematical models, and every unexpected observation raises new questions. What's fascinating is that these discoveries are not necessarily overturning the standard model. In many cases, they are revealing how much complexity was hidden inside a theory scientists thought they understood reasonably well. Imagine studying a city from an airplane. From high above, everything looks organised and predictable. Roads connect buildings, neighbourhoods follow patterns. But when you walk through the streets, you discover details that were invisible from the sky. Unexpected shortcuts, hidden alleyways, entire districts you never noticed before. That is somewhat similar to what CERN is revealing. The standard model remains remarkably successful, but its internal landscape appears far richer than physicists once realised. And this creates an intriguing possibility. If nature is producing exotic particles that researchers never expected to study in such detail, what else might be hiding in the data? Could even stranger combinations exist? Could unknown forms of matter be waiting just beyond current detection limits? Could some of these observations eventually point toward entirely new physics? No one knows yet. What scientists do know is that the particle zoo keeps growing. The deeper they look, the more variety they find. And every new discovery reinforces a lesson that has appeared repeatedly throughout the history of science. The universe is rarely as simple as it first appears. Just when researchers think they understand the rules, nature reveals another layer of complexity hiding underneath. Among all the mysteries facing modern physics, one stands above the rest in terms of sheer importance. Why is there something instead of nothing? At first that sounds like a philosophical question, but physicists can approach it scientifically because the laws of nature make a very specific prediction about the early universe. According to our best understanding of the Big Bang, enormous amounts of energy were converted into matter and antimatter. Antimatter is often described as the mirror image of ordinary matter. For every particle of matter, there is a corresponding antimatter version with opposite properties. An electron has a positively charged antimatter counterpart called a positron. Protons have antiprotons. Many other particles have antimatter equivalents as well. The strange thing is that matter and antimatter are extremely destructive when they meet. They annihilate each other and convert their mass back into energy. This creates a serious problem. If the Big Bang produced equal amounts of matter and antimatter, almost everything should have disappeared. The early universe would have become a giant battlefield of mutual annihilation. Matter would destroy antimatter. Antimatter would destroy matter. In the end, very little would remain. Yet that clearly isn't what happened. The stars overhead are made of matter. The earth is made of matter. Every person who has ever lived is made of matter. Somehow, matter won, and physicists have spent decades trying to understand why. The fact that matter survived means there must have been a tiny imbalance somewhere in the earliest moments of cosmic history. For every billion antimatter particles, perhaps there were 1,000,000,001 matter particles. That tiny excess would have been enough. After nearly all matter and antimatter annihilated each other, the leftover matter became everything we see today. The question is what created the imbalance. This is where CERN enters the story once again. One of the most important areas of research at the Large Hadron Collider involves studying subtle differences between matter and antimatter. Physicists refer to these differences as CP violation. The name sounds complicated, but the basic idea is straightforward. If the laws of physics treated matter and antimatter perfectly equally, they would behave in exactly the same way. In reality, experiments have shown small differences. Certain particles decay slightly differently than their antimatter counterparts. Those differences may seem minor, but they could be incredibly important. Without them, the universe we know may never have existed. Scientists have known about some forms of CP violation for decades. The problem is that the known effects appear too small. When researchers run the numbers, the amount of asymmetry predicted by the standard model doesn't seem large enough to explain the overwhelming dominance of matter we observe today. Something appears to be missing, and that missing ingredient could represent entirely new physics. Over the last several years, CERN experiments have been measuring these effects with unprecedented precision. Instead of focusing only on simpler particle systems, researchers have expanded their investigations into more complex particles that contain heavy quarks. These measurements are providing valuable new information about how matter and antimatter behave under different conditions. What makes this work so exciting is that even a small discrepancy could have enormous implications. Imagine discovering that a ruler you've trusted your entire life is slightly inaccurate. The error might be tiny, but if every measurement depends on that ruler, the consequences become significant. Similarly, if scientists uncover behavior that deviates from standard model predictions, it could point toward new particles, unknown interactions, or hidden mechanisms that operated during the universe's earliest moments. In other words, these experiments are not simply studying particle decays, they are investigating one of the most important events in cosmic history. The moment matter gained the upper hand. Think about what is really at stake here. Every galaxy exists because matter survived. Every star exists because matter survived. Every planet, ocean, tree, animal, and human being exists because matter survived. The entire visible universe depends on a slight imbalance that occurred billions of years ago. Yet nobody fully understands how that imbalance emerged. That is why physicists become excited when new measurements reveal even the smallest clues. A tiny anomaly in a detector could eventually lead to an explanation for one of the biggest mysteries in science. And if that explanation requires new physics beyond the standard model, the consequences could be enormous. It would mean that some of the most important processes in cosmic history are still missing. from our current theories. That possibility is both thrilling and unsettling, because it suggests that the reason we exist may depend on laws of nature we have not discovered yet. Somewhere in the vast collection of data pouring out of CERN could be a clue not merely about particles, not merely about forces, but about why there is a universe filled with matter at all. And until scientists solve that mystery, one of the most fundamental questions in existence remains unanswered. At first glance, antimatter sounds like one of the strangest ideas in science, a mirror version of matter. Particles that look almost identical to ordinary particles, but carry opposite charges. It feels like something invented for a science fiction story. Yet antimatter is completely real. Scientists create it in laboratories. Medical scanners use antimatter particles every day. Cosmic rays constantly produce antimatter high in Earth's atmosphere. The existence of antimatter is not controversial. The mystery is why there is so little of it. As we saw in the previous chapter, the universe should have begun with nearly equal amounts of matter and antimatter. According to current theories, the extreme energies present shortly after the Big Bang would naturally create both. Nature appears to have no reason to strongly favour one over the other, and yet when astronomers look out into space, they find a universe overwhelmingly dominated by matter. This creates a puzzle that becomes more frustrating the more scientists investigate it, because every new measurement seems to confirm two things at once. First, physicists know matter and antimatter do not behave in exactly the same way. Second, the differences they have found still do not appear large enough here to explain reality. That combination is deeply unsettling. If matter and antimatter were perfectly symmetrical, physicists would know exactly what the problem was. They would simply need to find the source of asymmetry. But nature has already revealed some asymmetry. The challenge is that it isn't enough. Imagine finding footprints at a crime scene. At first you think you've solved the case. Then you realise the footprints account for only 10% of what happened. Now you're left with an even bigger mystery. That's where antimatter research stands today. Scientists have found clues. They just haven't found enough clues. One major area of investigation involves studying particles and their antimatter counterparts with extraordinary precision. CERN has become one of the world's leading centres for this work. Researchers create particles, create antiparticles, and compare their behaviour in minute detail. Do they decay at exactly the same rate? Do they respond identically to physical forces? Do they obey every known symmetry of nature? These questions may sound technical, but they strike at the heart of why the universe exists, because even the smallest difference could point toward the mechanism that allowed matter to survive. Over the years, experiments have repeatedly confirmed that matter and antimatter are remarkably similar. In many situations, they appear almost indistinguishable, and that is part of the problem. The similarities are so strong that they make the observed dominance of matter difficult to explain. The universe seems to be telling two contradictory stories. One story says matter and antimatter should be nearly equal. The other story says matter somehow achieved overwhelming dominance. Reconciling those stories has become one of the biggest challenges in modern physics. What makes the situation even more intriguing is that antimatter itself may hold clues about entirely new physics. Researchers have begun studying antimatter with levels of precision that would have seemed impossible a few decades ago. They can trap antiatoms. They can examine how antimatter responds to electromagnetic fields. They can compare the properties of matter and antimatter with astonishing accuracy. So far, the results have largely confirmed existing theories, but every confirmation creates another layer of tension, because if the known differences remain too small, then something else must have happened. Some additional process may have existed in the early universe. Some unknown particle may have influenced cosmic evolution. Some hidden interaction may have temporarily tipped the balance toward matter. The frustrating reality is that scientists do not know which possibility is correct. This uncertainty has led many researchers to suspect that the standard model is missing a crucial piece of the puzzle. Not a minor correction, not a small adjustment, a genuinely new ingredient. And if that ingredient exists, it may be connected to several other mysteries at the same time. Dark matter, hidden particles, unknown forces, the early history of the universe. These problems may appear unrelated today, but nature often surprises us by connecting seemingly separate phenomena. The history of science is full of examples where one discovery solved multiple mysteries simultaneously. Many physicists hope the antimatter problem may eventually lead to a similar breakthrough. For now, however, the mystery remains stubbornly unsolved. The more precisely researchers study antimatter, the more they realise how difficult the challenge really is. Instead of moving closer to a complete explanation, they often find new layers of complexity, and that is what makes the situation so fascinating. The universe contains billions of galaxies. Each galaxy contains billions of stars. All of that structure exists because matter survived an event that should have destroyed it. Somewhere in the earliest moments of cosmic history, reality took a path that allowed everything we know to emerge. Scientists can see the outcome, they can measure the consequences, but the critical event itself remains hidden. And until physicists discover what gave matter the advantage, one of the most important chapters in the story of the universe remains unwritten. There is a reason many physicists describe quantum mechanics as the strangest successful theory ever created. It works. Its predictions are incredibly accurate. Modern technology depends on it. Yet some of its most fundamental ideas still sound completely absurd when you first hear them. Few concepts illustrate that better than quantum entanglement. Albert Einstein famously disliked the idea. He referred to it as spooky action at a distance because it seemed to violate common sense. Even today, entanglement remains difficult to visualize, but the basic idea is surprisingly simple. Imagine two particles becoming linked in such a way that they share a common quantum state. Once that connection forms, measuring one particle provides information about the other, even if the particles are separated by enormous distances. Importantly, this does not allow faster-than-light communication, but it does reveal that the quantum world operates very differently from our everyday experience. For decades, entanglement was mostly studied in highly controlled laboratory environments. Scientists worked with photons, electrons, or carefully isolated quantum systems. These experiments demonstrated that entanglement was real. The phenomenon was repeatedly verified. Yet many researchers viewed it as something associated with delicate quantum setups, a fragile effect that existed under special conditions. Then particle physicists started finding evidence that reality might be much stranger. Recent experiments have suggested that quantum entanglement can survive in environments that appear almost impossibly chaotic, including the violent particle collisions taking place inside the Large Hadron Collider. To understand why this is surprising, consider what happens during a proton collision. Two particles travelling at nearly the speed of light smash together. Energy explodes outward. New particles are created. Complex interactions occur within incredibly small fractions of a second. From a human perspective, it resembles complete disorder. If there were any place where delicate quantum relationships should disappear, this would seem to be it. Yet researchers increasingly suspect that entanglement remains present even within this apparent chaos. In some studies, scientists have observed patterns suggesting that quarks and other particles emerging from high-energy collisions retain quantum connections. These observations are still being investigated, but they have generated significant interest because they challenge older assumptions about how quantum systems behave. The implications extend far beyond particle physics. For years, many scientists treated quantum mechanics and large-scale reality as somewhat separate domains. Quantum effects dominated the microscopic world. Classical physics described the macroscopic world. The boundary between them was often blurry, but the distinction remained useful. Entanglement at extreme energies complicates that picture. It suggests quantum behavior may be woven more deeply into reality than previously imagined. Instead of disappearing in complex systems, quantum relationships may continue influencing events in subtle ways. The possibility has attracted attention from researchers working in several different fields. Some scientists study quantum information, others investigate black holes, others explore the nature of space-time itself. Surprisingly, many of these areas are becoming connected through the concept of entanglement. In recent years, some theoretical physicists have even proposed that space-time and gravity may be linked to underlying networks of quantum entanglement. These ideas remain speculative, but they illustrate how central entanglement has become to modern discussions about the foundations of reality. And that is part of what makes CERN's observations so interesting. The Large Hadron Collider was originally designed to explore fundamental particles. Now it is also providing insights into some of the deepest questions in quantum physics. Questions about information, questions about reality, questions about how the universe organizes itself at its most basic level. The truly fascinating aspect is that none of this was expected when the collider was first conceived. Scientists built the LHC to search for particles like the Higgs boson and to investigate the Standard Model. Instead, the machine is helping researchers explore entirely new areas of physics. And once again, the results are creating more questions than answers. Why does entanglement survive under such extreme conditions? How fundamental is it to the structure of reality? Could it help explain phenomena that remain mysterious today? Could it even play a role in unifying different areas of physics? At the moment, no one knows, but a pattern is beginning to emerge. Every time scientists push deeper into nature, they encounter layers of complexity they did not anticipate. First came the discovery that matter is made of atoms. Then atoms contained subatomic particles. Then those particles revealed quantum behavior. Now even quantum behavior itself appears richer and more interconnected than researchers once believed. The unsettling lesson is that reality may not be built from isolated objects at all. It may be built from relationships, connections, invisible links that exist beneath the surface of what we observe. And if that idea turns out to be true, then the universe could be far stranger than any simple collection of particles and forces. The discoveries emerging from CERN suggest we may still be looking at only part of the picture. The deeper structure remains hidden. But with every collision, scientists are uncovering clues that point toward something much larger waiting underneath. Up to this point, we've been discussing mysteries that physicists know exist. Dark matter, dark energy, the matter-antimatter imbalance, the challenge of unifying gravity with quantum mechanics. But there is another possibility that is even more unsettling. What if these problems are not separate mysteries at all? What if they are symptoms of something much larger, something hidden, something existing alongside the familiar universe, but largely invisible to us? This idea has become increasingly popular among physicists in recent years, and it goes by several names. The hidden sector, the dark sector, hidden physics. The exact terminology varies, but the basic concept is surprisingly simple. Imagine living in a city where you can see only 5% of the population. The remaining 95% exists around you, but cannot be observed directly. You would notice strange effects. Traffic patterns wouldn't make sense. Buildings would appear crowded, despite looking empty. Resources would disappear without explanation. You would constantly observe consequences without seeing their true cause. That situation resembles modern cosmology. Scientists can measure gravity throughout the universe. They can track how galaxies move. They can observe how cosmic structures evolve over billions of years. And everywhere they look, the visible matter appears insufficient to explain what's happening. Something else seems to be influencing events. The simplest explanation may be that there are entire categories of particles we have not discovered yet, not because they are rare, not because they are far away, but because they interact with ordinary matter so weakly that detecting them becomes extraordinarily difficult. This is where the idea of a hidden sector becomes fascinating. The standard model describes the particles and forces we know, but nature never promised that these are the only particles and forces that exist. There could be additional particles beyond our current detectors, additional forces beyond our current experiments, entire collections of matter that rarely interact with the world we experience. In some theoretical models, dark matter itself may belong to such a hidden sector. Instead of being a single mysterious particle, dark matter could be part of an entire invisible ecosystem. There might be dark particles interacting with other dark particles, dark versions of forces, dark structures, perhaps even forms of complexity we have not imagined. To be clear, these ideas remain speculative. Scientists do not yet have direct evidence for such hidden sectors, but what makes them attractive is that they could potentially explain multiple mysteries simultaneously. Dark matter becomes easier to understand. The matter-antimatter problem may acquire new solutions. Certain, unexplained, experimental anomalies could fit into a larger framework, and that possibility has motivated researchers at CERN to search in new ways. Historically, particle physicists often looked for dramatic discoveries. A new particle appears, a detector records a clear signal. A major breakthrough follows. Today, many searches are becoming subtler. Researchers are looking for missing energy, unexpected decay patterns, tiny statistical deviations, signs that particles may be interacting with something invisible. Think about it this way. If an unknown particle escapes a detector without leaving a trace, scientists might still infer its existence by observing what is missing. A collision begins with a known amount of energy. If some energy disappears unexpectedly, it may indicate that an unseen particle carried it away. This approach has become one of the most important strategies in modern particle physics, because if hidden sectors exist, they may not reveal themselves directly. Their presence might be detected only through indirect effects. The challenge is that nature has not made the search easy. So far, evidence remains frustratingly inconclusive. Many promising signals have eventually disappeared after additional analysis. Other anomalies remain intriguing, but not definitive. The situation has forced physicists into unfamiliar territory. Instead of narrowing possibilities, new data often expands them. The more researchers search, the more potential explanations emerge. Yet that uncertainty may actually be a clue. Historically, major scientific revolutions often began when observations stopped fitting existing frameworks. Astronomers once believed Earth occupied the centre of the cosmos. Unexpected observations challenged that view. Physicists once believed atoms were indivisible. Experiments proved otherwise. Today, scientists may be approaching another turning point, not because the standard model is failing completely, but because reality appears larger than the standard model can describe. The possibility changes the way many researchers think about the universe. The goal is no longer simply to discover a missing particle. The goal may be to uncover an entire hidden layer of reality, a layer that has been influencing the cosmos since the beginning of time, while remaining almost completely invisible. If such a sector exists, it would represent one of the biggest discoveries in scientific history, not an adjustment to our understanding of the universe, a transformation of it. And the unsettling possibility is that it may already be all around us. We just haven't learned how to see it yet. For decades, dark matter seemed like a problem that was waiting to be solved. Scientists knew it existed. They had overwhelming evidence for it. The only remaining challenge appeared to be identifying the particle responsible. Many researchers assumed that once experiments became powerful enough, the answer would emerge naturally. That is not what happened. Instead, dark matter has become one of the most frustrating mysteries in modern science. Not because the evidence for it has weakened. The evidence is stronger than ever. The problem is that every major search has come up empty, and the longer that continues, the stranger the situation becomes. To understand why, imagine discovering footprints in fresh snow. You can clearly see that someone walked through the area. The tracks are obvious, you know something was there, but no matter how carefully you search, you never find the person who left them. That is essentially the dark matter problem. Physicists can see its gravitational fingerprints everywhere. Galaxies rotate too quickly. Galaxy clusters contain too much gravity. Large-scale cosmic structures form in ways that require additional mass. Even observations of the early universe support the existence of dark matter. The evidence comes from multiple independent directions. The case is incredibly strong, yet the particle itself remains invisible. For many years, one candidate dominated discussions, a hypothetical particle known as a WIMP. The name stands for weakly interacting massive particle. The idea was appealing because it solved several problems at once. WIMPs would be heavy enough to provide the missing mass required by galaxies. They would interact weakly with ordinary matter, explaining why they are difficult to detect. And some leading theories, beyond the standard model, naturally predicted particles with exactly these properties. Many physicists believed WIMPs were the answer, so experiments were designed specifically to find them. Massive underground detectors were built. Sensitive instruments searched for rare interactions between dark matter and ordinary matter. Particle accelerators looked for signs that WIMPs might be produced. During high-energy collisions, researchers spent years refining their techniques. The expectation was straightforward. Sooner or later, evidence would appear. Instead, nothing happened. The detectors became more sensitive. Nothing. The datasets became larger. Nothing. The analyses became more sophisticated. Still nothing. At first, this wasn't alarming. Negative results are common in science. Researchers simply adjusted their models and continued searching. But as years passed, the situation became increasingly uncomfortable. Many of the most promising regions of parameter space were eliminated. Theories that once looked compelling lost support. Popular predictions failed one after another. The expected dark matter particle seemed to be vanishing. This is where CERN enters the story. One of the major goals of the Large Hadron Collider has been searching for evidence of particles beyond the standard model, including potential dark matter candidates. If dark matter particles could be produced in high-energy collisions, the LHC might detect their presence indirectly. Scientists searched carefully, yet despite enormous amounts of data, no definitive dark matter signal has emerged. That doesn't mean dark matter doesn't exist. Far from it. It means reality may be more complicated than physicists originally assumed. The failure to find WIMPs has forced researchers to broaden their thinking. Today, dark matter candidates span an enormous range of possibilities. Some proposed particles are far lighter than earlier theories suggested. Others may interact so weakly that existing detectors struggle to observe them. Some models involve entirely hidden sectors of physics, as we discussed in the previous chapter. Others propose that dark matter consists of multiple particle types rather than a single species. The field has become much more diverse, and oddly enough, that diversity may represent progress, because every failed search teaches scientists something important. A null result is still a result. It tells researchers where dark matter is not. It eliminates possibilities. It narrows the search. In some cases, these failures may be more informative than discoveries would have been. Imagine searching a massive maze. Every dead end removes one incorrect path. Eventually, the remaining options become clearer. That is increasingly how physicists view dark matter research. The absence of evidence is helping reshape the entire field. Still, there is something unsettling about the situation. Dark matter appears to dominate the universe's matter content. Its gravitational influence helps shape galaxies and cosmic structures. Without it, the universe would look completely different. And yet humanity still does not know what it is. Think about how extraordinary that statement is. One of the most important components of the cosmos remains unidentified. The largest machines ever built have searched for it. The most sensitive detectors ever constructed have searched for it. Entire scientific careers have been devoted to finding it, and the mystery remains. That is why some physicists now speak of the dark matter failure, not because the search has failed completely, but because many of the assumptions that guided the search for decades appear increasingly uncertain. The universe clearly contains something hidden. The evidence leaves little room for doubt. The real question is whether scientists have been looking for the right thing, and the longer dark matter remains invisible, the more likely it becomes that the answer is far stranger than anyone originally imagined. When the Higgs boson was finally discovered in 2012, many people viewed it as the end of a long scientific journey. For particle physicists, it was the missing piece of the standard model. A particle that had been predicted decades earlier had finally been found. The discovery was so important that it quickly became one of the most celebrated achievements in modern science. But more than a decade later, scientists have come to realize something surprising. The Higgs boson solved one major problem and exposed several new ones. To understand why, we need to remember what made the Higgs so important in the first place. Before the Higgs mechanism was proposed, physicists faced a serious challenge. Their equations suggested that fundamental particles should be massless. If that were true, electrons would race through the universe at the speed of light. Atoms could not form, chemistry would not exist, life would be impossible. Clearly something was missing. The solution was the Higgs field. According to the theory, an invisible field fills all of space. As particles move through this field, they acquire mass. Some interact strongly and become heavy. Others interact weakly and remain light. The Higgs boson is the detectable signature of that field. Finding it confirmed that the mechanism works, and that was a tremendous success. But science has a habit of turning solutions into new mysteries. Once physicists had the Higgs, they could begin studying it in detail, and that is where things became interesting. The first surprise was how ordinary the Higgs appeared. Many researchers had hoped it would immediately point toward new physics. Perhaps it would interact with unknown particles. Perhaps its properties would deviate from theoretical predictions. Perhaps it would provide clues about dark matter or hidden dimensions. Instead, the Higgs behaved remarkably well, almost too well. Measurements after measurement showed that it closely matched standard model expectations. At first this seemed like good news, but over time it became a source of frustration. Because the standard model is known to be incomplete, physicists expected the Higgs to provide a doorway beyond it. Instead, that doorway remained stubbornly closed. Then researchers encountered a deeper problem. The Higgs itself appears strangely unnatural. This issue is sometimes called the hierarchy problem. The details are mathematically complex, but the basic idea can be understood without advanced physics. According to quantum mechanics, empty space is not truly empty. Even a vacuum contains countless quantum fluctuations. Particles constantly appear and disappear at microscopic scales. These fluctuations should influence the Higgs boson, and according to many calculations, they should drive its mass to enormously larger values than what scientists actually observe. Yet somehow that does not happen. The Higgs mass sits in a narrow range that appears surprisingly stable. To make the equations work, physicists often have to introduce delicate cancellations. The numbers must balance with extraordinary precision. Many researchers find this uncomfortable. Nature can certainly be precise, but such extreme balance in acts often suggests that something deeper is going on. Historically apparent fine-tuning has sometimes pointed toward undiscovered physics. This led to one of the biggest expectations surrounding the Large Hadron Collider. Scientists believed new particles might appear that naturally stabilize the Higgs. These particles would solve the hierarchy problem and explain why the Higgs has the properties it does. For years, researchers searched intensely, yet those particles never appeared. The Higgs remained alone, and that absence created another mystery. Why does the Higgs seem so finely tuned if the mechanisms expected to stabilize are nowhere to be found? The questions don't stop there. The Higgs field is also unique because it fills the entire universe. Every atom, every star, every galaxy, everything exists within this field. That means understanding the Higgs is not simply a particle physics problem. It is a question about the structure of reality itself. What determines the strength of the field? Why does it have the value it does? Could it interact with unknown particles? Could it connect to dark matter? Could it be part of a larger hidden framework? Scientists do not yet know. This uncertainty has transformed the Higgs boson from a solved problem into an active area of research. Today, CERN's experiments are measuring its properties with ever-increasing precision. Researchers examine how often it decays into different particles. They study how it interacts with heavy quarks and leptons. They search for tiny deviations that might reveal new physics lurking beneath the surface, and the stakes are enormous because the Higgs occupies a special position within the standard model. It is unlike any other known particle. If hidden physics exists, the Higgs may be one of the best places to find evidence of it. That is why physicists continue to scrutinize every detail. The discovery itself was historic, but the real story may be what comes next, because after more than a decade of study, the Higgs boson has delivered a strange message. We found the particle we were looking for, yet we still do not fully understand why it exists in the form that it does. And that means one of the most important discoveries in modern science may still be hiding some of its biggest secrets. So far, we've discussed mysteries involving dark matter, antimatter, hidden particles, and the Higgs boson. But there is another problem that many physicists consider even more unsettling. Not because it involves something unknown, but because it involves empty space itself, at least what we call empty space. Most people imagine a vacuum as nothingness, a completely empty region containing no matter, no energy, and no activity. Modern physics paints a very different picture. According to quantum theory, empty space is not truly empty. Even a perfect vacuum is filled with quantum fields. These fields exist everywhere in the universe. Particles emerge from them. Forces arise from them. Every object around you ultimately depends on their existence. In a sense, the vacuum is less like an empty void and more like an invisible ocean underlying reality. And that ocean may contain one of the biggest problems in all of physics. To understand why, imagine placing a ball in a valley. If the ball sits at the lowest point, it is stable. Small disturbances won't change much because the ball is already in the minimum energy position available. Now imagine placing the ball in a shallow depression near the top of a mountain. At first it appears stable. It can remain there for a long time, but it isn't truly secure. A sufficiently large disturbance could send it rolling downward into a deeper valley. The system would suddenly transition into a more stable state. Physicists use a similar idea when discussing quantum fields. The concern is that our universe may not occupy the lowest possible energy state. Instead, it may exist in what is called a false vacuum. A false vacuum is a state that appears stable, but isn't the ultimate minimum. There could, in principle, be a deeper and more stable vacuum state, hidden beneath the one we currently inhabit. If that sounds abstract, consider the implications. The laws of physics depend on the values of various fields throughout the universe, the masses of particles, the strengths of forces, the structure of atoms. All of these properties emerge from the underlying vacuum state. If the vacuum changed, those properties could change as well. The universe would become fundamentally different. Atoms might no longer remain stable. Chemistry could cease to function. Matter itself could be altered. The terrifying aspect is that such a transition, if it were possible, would spread at the speed of light. Nothing could outrun it. Nothing could warn us in advance. One moment the universe would operate according to familiar laws. The next, an expanding bubble of a new vacuum state would rewrite reality wherever it passed. Now, before anyone panics, there is an important point to understand. This is not something scientists expect to happen tomorrow, or next year, or likely any time in the foreseeable future. The idea comes from theoretical calculations, not direct evidence that vacuum decay is imminent. In fact, if our universe is metastable, it may remain that way for periods vastly longer than the current age of the cosmos. The concern is not practical danger. The concern is what these calculations reveal about reality. And surprisingly, the Higgs boson plays a central role. After the Higgs was discovered, physicists could finally perform more detailed analyses of the vacuum structure associated with the Higgs field. When they plugged the measured values into their equations, the results were unexpected. The numbers placed our universe in a curious position, not obviously stable, not obviously unstable, but very close to the boundary between the two. This finding attracted enormous attention because it raised a profound question. Why does nature appear balanced so delicately? Many physicists expected the parameters of the universe to fall comfortably within a stable region. Instead, reality seems to sit near a critical threshold. Some researchers view this as a coincidence. Others suspect it may be hinting at deeper physics. Perhaps unknown particles influence the Higgs field. Perhaps hidden forces alter the calculations. Perhaps the standard model is incomplete in ways that affect vacuum stability. Once again, scientists do not yet know. What makes the situation especially fascinating is that the vacuum problem connects to many other mysteries. The Higgs boson, quantum fields, the earliest moments after the Big Bang, the fundamental structure of space-time. Questions that initially appear unrelated may actually be intertwined. And that possibility has transformed the vacuum from a technical detail into one of the most important subjects in theoretical physics. The deeper researchers investigate, the stranger the picture becomes. What we casually call empty space may actually be one of the most dynamic and significant components of reality. Everything we know exists within it. Every star, every planet, every living thing. Yet scientists still struggle to understand its true nature. That realization is perhaps the most unsettling part. The ground beneath our feet feels solid. The universe appears stable. Reality seems permanent. But modern physics suggests those impressions may be misleading. Beneath everything we see lies a quantum vacuum whose deepest properties remain mysterious. And despite decades of progress, humanity still doesn't fully understand the foundation upon which the entire universe is built. For much of the last 40 years, many physicists believed they already had a strong candidate for what lies beyond the standard model. The theory was called supersymmetry, and for a long time, it seemed almost too good to be wrong. Supersymmetry, often shortened to SUSY, proposed a remarkably elegant idea. According to the theory, every known particle has a hidden partner. Electrons would have partner particles, quarks would have partner particles, photons would have partner particles, even the Higgs boson would have additional counterparts. These partner particles would not simply double the number of known particles. They would help solve several major problems that physicists had been struggling with for decades. That was the beauty of the idea. One theory appeared capable of addressing multiple mysteries at once. First, supersymmetry offered a potential solution to the Higgs hierarchy problem. As we discussed in the previous chapter, quantum fluctuations should push the Higgs mass toward enormous values. Supersymmetric particles could cancel out those effects naturally, keeping the Higgs stable without requiring extreme fine-tuning. Second, supersymmetry provided promising dark matter candidates. Some supersymmetric particles would be stable, electrically neutral, and difficult to detect. Those properties made them ideal candidates for the invisible matter that appears to dominate galaxies. Third, the theory improved efforts to unify the fundamental forces. When physicists extended their equations using supersymmetry, the strengths of certain forces lined up more neatly at extremely high energies. For many researchers, this was exactly the kind of elegance they expected nature to favour. The theory was mathematically attractive. It solved important problems. It generated testable predictions. And most importantly, it suggested that new particles should eventually become visible at sufficiently high energies. This created enormous excitement when plans for the Large Hadron Collider were being finalised. Many scientists believed the LHC would discover supersymmetry relatively quickly. The reasoning seemed straightforward. If supersymmetric particles existed near the energy scales required to stabilise the Higgs boson, the collider should have a realistic chance of producing them. Researchers spent years developing search strategies. Entire careers were built around supersymmetric models. By the time the LHC switched on, expectations were high. Then the data started arriving. Nothing. The collider collected more collisions. Nothing. The energy increased. Nothing. Run after run passed. Still nothing. At first, physicists were not overly concerned. The simplest versions of supersymmetry might have been wrong, but more complicated versions remained possible. The predicted particles could simply be heavier than expected. The theory still had room to survive, but as the years passed, the situation became increasingly uncomfortable. The LHC continued exploring regions where many researchers had expected supersymmetry to appear. Those regions became empty. Models that once seemed natural required growing amounts of adjustment. The elegant simplicity that originally attracted scientists to the theory began to fade, and that created a psychological shift within the physics community. For decades, supersymmetry had been viewed as one of the leading candidates for new physics. Many researchers expected it to guide the next generation of discoveries. Instead, the theory found itself under pressure from reality. This does not mean supersymmetry has been disproven. That point is important. The theory remains mathematically viable in many forms. Some supersymmetric particles could exist at energies beyond the reach of current experiments. Others might interact in ways that make them harder to detect. Researchers continue searching. The story is not over, but confidence has changed. Before the LHC, many physicists asked, which version of supersymmetry will we find? Today, many are asking, does supersymmetry exist at all? That difference is enormous. It reflects a broader transformation occurring throughout particle physics. For years, researchers had a roadmap. They expected the standard model to be incomplete. They expected supersymmetry to emerge. They expected dark matter candidates to appear. The future seemed relatively clear. Then the experiments refused to cooperate. And this is where the real significance of supersymmetry's absence becomes apparent. The failure to find expected particles may be as important as finding new ones. Science advances by comparing theory with observation. When observations disagree with expectations, scientists are forced to rethink their assumptions. Sometimes that leads to small corrections. Sometimes it leads to revolutions. History offers many examples. Scientists once expected planets to move according to one set of rules until observations forced a new understanding. Physicists once expected atoms to behave classically until experiments revealed quantum mechanics. Today, particle physics may be approaching a similar crossroads. The missing supersymmetric particles have become a mystery of their own, not because scientists know the theory is wrong, but because one of the field's most promising ideas has repeatedly failed to reveal itself. And every year that passes without evidence makes the silence more significant. The universe does not care how elegant a theory appears. It does not reward mathematical beauty. Nature follows its own rules, and if those rules are different from what physicists expected, then the next breakthrough may come from a direction nobody anticipated. That possibility is both exciting and unsettling, because it means the future of fundamental physics may be far less predictable than researchers once believed. Science is often portrayed as a steady march toward truth. A scientist proposes an idea, experiments confirm it, knowledge advances. Reality is usually messier than that. Some of the biggest breakthroughs in history happened because experiments refused to behave the way scientists expected. The orbit of Mercury didn't match predictions, helping lead to Einstein's theory of general relativity. Classical physics couldn't explain certain atomic phenomena, contributing to the birth of quantum mechanics. Unexpected observations of distant galaxies revealed that the universe is expanding. Again and again, progress emerged from disagreement. And today, particle physics finds itself in a strangely familiar situation. The problem is not that scientists lack theories. If anything, they have too many. For decades, physicists developed sophisticated mathematical frameworks designed to extend the standard model. Supersymmetry, extra dimensions, hidden sectors, various dark matter models, countless alternatives and variations. Many of these ideas appeared promising. Some solved multiple theoretical problems simultaneously. Others provided elegant explanations for unexplained observations. Researchers expected experiments to gradually sort through the possibilities. Certain theories would survive, others would fail. The field would move forward, but reality had other plans. Instead of producing a clear winner, modern experiments have often eliminated the simplest and most popular explanations. This has created a peculiar tension throughout fundamental physics. The standard model continues passing test after test. At the same time, everyone knows it cannot be complete. The theories designed to replace or extend it have largely failed to reveal themselves. As a result, physicists occupy an unusual middle ground. They know something is missing, but they do not know what. Imagine working on a giant jigsaw puzzle. You can clearly see an empty space in the middle. You know pieces belong there. The shape proves it. Yet none of the available pieces fit. That is increasingly how many researchers describe the current state of particle physics. The gaps are obvious. Dark matter exists. Dark energy exists. Gravity remains disconnected from quantum mechanics. The matter-antimatter imbalance remains unexplained. Yet the expected solutions keep refusing to appear. This has led some physicists to question assumptions that once seemed almost unquestionable. Perhaps nature is not organised according to principles that researchers considered natural. Perhaps simplicity is not always the correct guide. Perhaps elegance is not a reliable indicator of truth. These may sound like philosophical concerns, but they have practical consequences. For many years, certain ideas dominated research because they appeared mathematically beautiful. Symmetry, in particular, played a major role. Physicists often assumed that deeper levels of reality would reveal increasingly elegant structures. Nature seemed to reward symmetry. Again and again, the standard model itself reflects this pattern. But recent experimental results have challenged that confidence. What if nature is not obligated to follow human ideas of beauty? What if the universe is stranger, messier, or more complicated than theorists expected? These questions are becoming increasingly difficult to ignore. The situation is not a crisis in the traditional sense. Science is still working. Experiments are still produced invaluable data. Theories are still being tested. But there is growing recognition that some long-held assumptions may need re-examination. Interestingly, many physicists see this as a positive development. Periods of uncertainty often precede major breakthroughs. When a scientific framework becomes too comfortable, progress can slow. Unexpected results force researchers to think differently. They encourage new ideas. They create opportunities for discoveries nobody anticipated. History suggests that these moments can be incredibly productive. The challenge is that they rarely feel productive at the time. For scientists working in the middle of such transitions, uncertainty can be frustrating. Years of work may produce more questions than answers. Promising theories may collapse under new evidence. Research paths that once seemed obvious may suddenly disappear. Yet that discomfort is often where the most important advances begin. The current generation of physicists may be experiencing exactly that kind of transition. The old roadmap is becoming less reliable. The expected discoveries are not arriving on schedule. Theoretical predictions and experimental reality are increasingly difficult to reconcile. And that forces a deeper question. What if the problem is not that scientists lack data? What if the problem is that they have been asking the wrong questions? That possibility is beginning to influence the direction of modern research. Instead of searching only for predicted particles, researchers are becoming more open to surprises. Instead of testing a handful of favoured theories, they're exploring broader possibilities. Instead of assuming they know what new physics should look like, they are allowing the data to speak more freely. This shift may prove crucial because history shows that nature often reveals its secrets in ways nobody expects. The greatest discoveries are rarely the ones scientists confidently predict. They are the ones that force an entirely new way of thinking. And if that pattern holds true once again, then the most important discovery waiting inside CERN's data may not confirm existing theories. It may overturn them. That prospect is unsettling. For some researchers, for others, it is exactly what makes this moment so exciting. Because when experiments stop matching expectations, science enters its most interesting phase, the phase where genuine revolutions become possible. One of the biggest challenges facing CERN today is not building more powerful machines. It's understanding the data those machines produce. The Large Hadron Collider generates an almost unimaginable amount of information. Every second, millions of particle collisions occur inside its detectors. Each collision creates a cascade of particles, energy signatures, and decay products. The raw data volume is so enormous that scientists cannot possibly examine every event individually. In the early days of particle physics, researchers could often inspect important events by hand. That era is long gone. Modern experiments operate on a scale that exceeds human capabilities. Even teams of thousands of scientists cannot manually search through everything the collider records. And that is where artificial intelligence enters the story. For years, machine learning systems have been quietly assisting particle physicists. At first, their role was relatively limited. They helped classify events. They improved data filtering. They accelerated calculations. But as AI technology became more sophisticated, researchers began realizing something important. These systems could identify patterns that humans might never notice, not because AI understands physics better than scientists, but because it can process vast quantities of information far faster than any person. Imagine trying to find a single unusual frame hidden inside millions of hours of video footage. A human would struggle. An advanced machine learning system can scan the entire dataset and flag unusual patterns in a fraction of the time. Particle physics presents a similar challenge. The signals researchers care about are often buried beneath enormous amounts of background noise. Rare events may occur only once in billions of collisions. Subtle deviations may be hidden inside complex statistical distributions. Finding them requires extraordinary precision. Machine learning has become increasingly valuable because it excels at recognizing complicated relationships within large datasets. Instead of searching only for specific signals predicted by existing theories, AI systems can be trained to identify events that simply appear unusual. This shift is significant. Historically, physicists often searched for phenomena they already expected to find. A theory predicts a particle. Scientists look for evidence of that particle. The process is logical and effective, but it carries a limitation. If nature produces something entirely unexpected, researchers may overlook it. After all, they were not looking for it. AI offers a different approach. Rather than focusing exclusively on known possibilities, machine learning systems can help identify anomalies that deserve further investigation. In a sense, they act as discovery assistants. They point scientists toward regions of data that appear interesting, even when nobody knows exactly what they represent. That capability is becoming increasingly important as physics enters a period of uncertainty. As we discussed in previous chapters, many anticipated discoveries have not appeared. Dark matter remains elusive. Supersymmetry remains unconfirmed. Several popular theoretical frameworks face growing challenges. Physicists can no longer assume they know what new physics will look like. This makes open-ended exploration more valuable than ever, and AI is particularly well suited for that task. Some researchers compare the situation to exploring an unfamiliar continent. Traditional searches follow established maps. Machine learning helps identify territories that do not appear on any map at all. Of course, AI is not performing science independently. This is an important distinction. The algorithms do not develop theories. They do not understand physical laws. They do not replace scientists. Human researchers still interpret results, design experiments, and determine whether potential discoveries are real. The role of AI is to expand human capabilities, to help researchers navigate data volumes that would otherwise be overwhelming. Yet even in this supporting role, the impact is becoming substantial. As CERN's datasets continue growing, machine learning is increasingly integrated into nearly every stage of analysis. Collision events are filtered using AI-assisted techniques. Particle identification is improved through machine learning models. Where signals become easier to isolate, computational efficiency increases dramatically, and future upgrades to the collider will make these tools even more important. The next generation of experiments will produce data at levels that push current methods to their limits. Without advanced computational approaches, extracting meaningful information would become nearly impossible. What makes this especially fascinating is the possibility that AI may help us uncover phenomena nobody predicted. Not because artificial intelligence possesses creativity in the human sense, but because it is capable of examining patterns at scales beyond ordinary perception. History shows that major discoveries often begin as anomalies, a small discrepancy, an unexpected signal, a result that doesn't fit existing theories. Those anomalies are easy to miss when datasets become enormous. Machine learning helps ensure they are not overlooked, and that creates an intriguing possibility. Somewhere within the trillions of collisions recorded at CERN may already be evidence of something extraordinary, a hidden particle, an unknown interaction, a clue pointing beyond the standard model. The signal could be present right now, buried beneath mountains of information. The challenge is finding it. For the first time in scientific history, researchers are partnering with machines capable of searching data on a scale no human team could manage alone. Whether that partnership leads to a revolutionary discovery remains uncertain. But one thing is clear: the future of particle physics will not be shaped solely by larger accelerators and better detectors. It will also be shaped by new tools that help scientists see patterns hidden within the deepest layers of reality. And those tools may eventually reveal secrets that have been hiding in plain sight all along. If the story ended with the current Large Hadron Collider, many physicists would already consider it one of the most successful scientific instruments ever built. It discovered the Higgs boson. It transformed our understanding of particle physics. It produced vast amounts of data and revealed countless new details about the subatomic world. But according to CERN's plans, the most productive years of the collider may still lie ahead, because the next chapter is not about building an entirely new machine. It's about turning the existing machine into something far more powerful. This project is known as the High Luminosity Large Hadron Collider, often abbreviated as the HLLHC. The name may sound technical, but the underlying idea is simple. Many people assume scientific progress comes from increasing energy. Higher energy means deeper exploration, and that is often true. But there is another way to improve a particle collider. Instead of making collisions dramatically more energetic, you can make them happen much more frequently. This is what physicists call luminosity. A collider with higher luminosity produces more collisions over time, and more collisions mean more opportunities to observe rare phenomena. Imagine trying to win a lottery. Buying one ticket gives you a chance. Buying 1 million tickets dramatically improves the odds. The high luminosity LHC follows a similar principle. Rather than relying on a small number of extraordinary events, it will generate vastly larger data sets, increasing the probability of capturing rare processes that current experiments might miss. The scale of the upgrade is enormous. Engineers are replacing key components throughout the accelerator complex. New magnets are being installed, detector systems are being upgraded, computing infrastructure is being expanded. Virtually every aspect of the scientific operation is being enhanced. The goal is ambitious. By the end of its planned lifetime, the upgraded collider is expected to collect several times more data than the current LHC has gathered during its entire operational history. That increase may sound like a simple numerical improvement. In reality, it could completely transform what scientists are able to study. Many important physical processes are incredibly rare. Some occur only once in billions of collisions. Others may occur even less frequently. Current datasets allow researchers to glimpse these events. Future datasets may allow them to measure them with precision. This distinction matters. Discovering a phenomenon is one thing. Understanding it is another. Take the Higgs boson as an example. Finding the particle was a historic achievement, but fully understanding its properties requires many more observations. Scientists want to know exactly how it interacts with other particles. They want to test whether its behavior deviates from standard model predictions. They want to determine whether subtle anomalies exist. These questions demand enormous amounts of data. The high luminosity LHC is designed to provide it. Dark matter searches may benefit as well. As we've discussed, no definitive dark matter particle has emerged from current experiments, but rare signals can easily hide within limited data sets. Increasing the number of collisions dramatically improves the chances of detecting faint signatures. The same applies to searches for hidden sectors, exotic particles, and unknown interactions. Many possibilities remain beyond the reach of existing statistics. Future data could change that. What's especially interesting is that the upgrade reflects a shift in how physicists think about discovery. In earlier decades, researchers often expected breakthroughs to arrive through dramatic new particles suddenly appearing. Today, many scientists believe the next revolution may emerge through precision, tiny deviations, subtle patterns, small discrepancies between prediction and observation. The larger the dataset becomes, the easier these effects are to detect. This means the high luminosity LHC is not merely a bigger experiment. It represents a different strategy. Instead of searching only for obvious signs of new physics, researchers are preparing to examine reality with unprecedented detail. And sometimes detail changes everything. History provides many examples. Astronomers improved their measurements and discovered that galaxies were moving away from one another. Physicists improved their measurements and uncovered quantum mechanics. Tiny discrepancies have often revealed enormous truths. The upcoming collider upgrade may continue that tradition. Of course, there are no guarantees. Nature is under no obligation to provide easy answers. Larger datasets may confirm existing theories. They may reveal new anomalies. They may expose entirely unexpected phenomena. Nobody knows. That uncertainty is precisely what makes the project so important. Because modern physics has reached a point where the biggest questions cannot be answered through speculation alone. Researchers need more evidence, more precision, more collisions, more opportunities to let reality reveal its secrets. The high luminosity LHC is designed to provide exactly that, and if hidden physics truly exists somewhere beyond the standard model, the upgraded machine may offer humanity its best chance yet to find it. The coming decade could determine whether today's mysteries finally begin to unravel, or whether the universe proves even stranger than physicists currently imagine. Either outcome would change the future of science. Scientists are trained to follow evidence wherever it leads. They do not get to choose what nature reveals. Still, every researcher has ideas about what they hope might be waiting beyond the current frontier. And when physicists talk privately about the discoveries they would most like to make, certain possibilities appear again and again, not because they are guaranteed to exist, but because they could answer some of the biggest questions in science. At the top of the list is dark matter. For decades, dark matter has remained the most obvious sign that something important is missing from our understanding of the universe. Researchers can see its gravitational effects across cosmic scales. They can measure its influence on galaxies and galaxy clusters, yet they still do not know what it is. Finding the particle responsible would instantly become one of the greatest discoveries in scientific history. It would solve a mystery that has persisted for generations. More importantly, it would reveal an entirely new category of matter. Imagine learning that everything visible in the universe represents only a small fraction of reality, and then finally discovering what makes up the hidden majority. That is the scale of the opportunity. Another major hope involves new fundamental forces. Most people are familiar with gravity and electromagnetism. Physicists also know about the strong and weak nuclear forces. Together, these four interactions shape the universe we observe. But there is no law stating that only four forces can exist. Additional forces may be hidden from us because they operate over very short distances, or interact only weakly with ordinary matter. Discovering a fifth fundamental force would radically alter physics. Entire areas of research would need to be reconsidered. The standard model would immediately require expansion, and previously unrelated mysteries might suddenly become connected. Then there is the possibility of extra dimensions. This idea often appears in science fiction, but it also emerges naturally within several serious theoretical frameworks. The concept is not that alternate worlds exist alongside ours in a fantasy sense. Rather, reality itself may contain additional spatial dimensions beyond the three we experience daily. If these dimensions exist, they could be hidden because they are extremely small, or because ordinary matter cannot move through them easily. Some theories suggest that gravity appears unusually weak compared to other forces because part of its influence extends into these unseen dimensions. At the moment, there is no direct evidence for extra dimensions, but if experiments at CERN were to uncover signs of them, the implications would be extraordinary. Our understanding of space would fundamentally change. The universe would become far larger and more complex than it currently appears. Many physicists are also interested in hidden sectors of reality. As we discussed earlier, the visible particles described by the standard model may represent only one part of a much larger system. There could be entire collections of particles and forces that interact only weakly with our familiar world. Dark matter might belong to such a sector. So might other unexplained phenomena. The discovery of hidden physics would force a dramatic revision of humanity's picture of reality. Instead of one particle family and four known forces, we might find ourselves living inside a far richer cosmic ecosystem. Then there are the hopes connected to unification. One of the oldest dreams in physics is the idea that all forces ultimately emerge from a deeper underlying principle. History offers some encouragement Electricity and magnetism were once considered separate phenomena before scientists discovered they are different aspects of the same force. Researchers have spent decades searching for similar connections among the fundamental forces. A successful unification theory would reveal relationships hidden beneath the surface of nature. It would show that seemingly different phenomena are part of a larger structure. Perhaps the most ambitious goal of all is understanding quantum gravity. Today, physics rests on two extraordinarily successful foundations. Quantum mechanics explains the microscopic world. General relativity explains gravity and large-scale cosmic structures. The problem is that these theories do not fit together cleanly. Somewhere deeper down, a more complete framework almost certainly exists. Physicists desperately want to find it, because solving that problem could reveal what space-time really is, what happened during the earliest moments of the Big Bang, and how reality operates at its most fundamental level. What connects all of these possibilities is a simple idea. Researchers are not merely searching for another particle. They are searching for a doorway leading beyond the standard model and into a deeper understanding of the universe. That is why the data emerging from CERN generates so much excitement. Every collision represents a chance that reality will reveal something unexpected, a chance that one anomaly will grow into a discovery, a chance that a mystery which has frustrated scientists for decades will finally begin to unravel. No one knows which breakthrough, if any, will arrive first, but nearly everyone agrees on one thing. If even one of these possibilities turns out to be real, the consequences will reach far beyond particle physics. They will change humanity's understanding of the universe itself. At first, this question sounds disappointing. What happens if CERN spends years collecting data, upgrading detectors, and analysing trillions of particle collisions, only to discover nothing new? Most people assume that would be a failure. In reality, many physicists believe it could be one of the most important outcomes imaginable, because nothing does not actually mean nothing. If the Large Hadron Collider continues operating at increasingly higher precision and still fails to reveal new particles, new forces, hidden dimensions, or clear deviations from the standard model, the implications would be profound. It would mean that many of the assumptions guiding theoretical physics for decades may be wrong. That possibility is difficult to appreciate because science is often associated with discoveries, new planets, new particles, new theories. But ruling out possibilities can be just as important. Imagine searching an entire building for a missing object. Room after room turns up empty. At first, this seems frustrating. Eventually, however, the empty rooms become valuable information. They tell you where the object is not. The search becomes more focused. The remaining possibilities become clearer. Physics works the same way. Every failed search eliminates ideas. Every null result narrows the range of acceptable explanations. And over time, those eliminations can completely transform a field. This process is already happening. For decades, many researchers expected new particles to appear relatively close to the energy scales explored by the Large Hadron Collider. The reasoning seemed reasonable. The standard model contains several features that appear finely tuned. Problems such as the Higgs hierarchy issue seem to suggest that additional physics should emerge nearby. Yet years of data have produced no definitive evidence for those expected solutions. The deeper scientists search, the more constrained many theories become. This creates an uncomfortable possibility. Perhaps the universe is not organised according to principles physicists assumed. Perhaps some of the concepts that guided research for generations are incomplete, or perhaps entirely new frameworks are needed. That would not be a failure. It would be a scientific revolution. History contains many examples where the absence of expected evidence changed everything. For centuries, astronomers believed planets moved in perfect circles. Observations eventually proved otherwise. Physicists once searched for a hypothetical substance called the luminiferous ether, believed to carry light waves through space. The failure to find it helped pave the way for Einstein's theories. Sometimes the most important discovery is learning that a cherished idea does not correspond to reality. Particle physics may be approaching a similar moment. Consider the implications. Suppose the high luminosity Large Hadron Collider gathers several times more data than current experiments. So suppose precision measurements continue improving. Suppose dark matter searches remain unsuccessful. Suppose supersymmetry remains absent. Suppose every result continues matching standard model predictions. At that point, physicists would face a difficult question. Why does a theory known to be incomplete describe nature so successfully? Remember, the standard model cannot explain dark matter. It cannot explain dark energy. It cannot fully account for the matter-antimatter imbalance. It does not incorporate gravity in a satisfactory way. The gaps remain. Yet if no new physics appears, those gaps become even more mysterious. The missing pieces would have to exist in forms far different from what researchers currently expect. That realization could trigger a major shift in scientific thinking. Instead of extending familiar theories, physicists might need entirely new approaches, new mathematical frameworks, new conceptual foundations, new ways of interpreting reality. Ironically, this outcome could be more disruptive than a straightforward discovery. Finding a new particle would answer a question. Finding nothing would challenge the questions themselves. And that distinction matters, because science advances not only by acquiring information, but also by improving the way problems are framed. When old assumptions stop working, researchers are forced to reconsider fundamentals. The process can be uncomfortable. It can take years, sometimes decades, but it often produces the most transformative breakthroughs. There is another reason why nothing would be significant. The universe has repeatedly surprised scientists throughout history. Again and again, reality has turned out to be stranger than expected. The absence of anticipated discoveries may simply be another example of that pattern. Perhaps nature's true structure lies in a direction few researchers have considered. Perhaps the answers are hidden in subtle effects rather than dramatic signals. Perhaps entirely new concepts are required. If so, every null result becomes a clue, not a dead end, a signpost, an indication that researchers must look elsewhere. This is why many physicists remain optimistic despite years of unanswered questions. The goal of science is not to prove favoured theories correct. The goal is to understand reality, and reality does not care what scientists expect, whether CERN discovers new particles or continues finding nothing unexpected. The data will still teach us something profound, because every answer narrows the possibilities, and every eliminated possibility brings humanity one step closer to understanding what the universe actually is. Sometimes the most revolutionary discovery is not what appears, it's what stubbornly refuses to appear. At the beginning of this video, we asked a simple question. What exactly has CERN discovered that should terrify us? Now, after everything we've explored, the answer is probably very different from what most people expected. The terrifying part is not a dangerous particle, not a black hole, not a portal to another universe, and not some experiment that threatens Earth. The real story is far stranger. The deeper scientists investigate reality, the less complete our understanding appears to be. Think about what we've learned. The standard model is one of the most successful scientific theories ever created. It predicts the behaviour of particles with extraordinary accuracy. It has passed countless experimental tests. It correctly anticipated discoveries that took decades to confirm, and yet it cannot explain some of the most important features of the universe. It does not explain dark matter. It does not explain dark energy. It does not explain why matter survived after the Big Bang. It does not provide a complete theory of gravity. In other words, humanity's greatest description of reality, leaves enormous portions of reality unexplained. That alone is remarkable. But the situation becomes even more unsettling when we consider what CERN has been finding. The Large Hadron Collider keeps producing data. More collisions, more precision, more opportunities to uncover hidden physics. Yet instead of delivering clear answers, it often reveals deeper mysteries. Expected particles remain missing. Popular theories face increasing pressure. The universe refuses to behave according to many of the assumptions physicists once considered reasonable. Again and again, nature seems to be saying the same thing. The story is more complicated than you think. That message appears everywhere, in the antimatter problem, in the dark matter mystery, in the strange behaviour of quantum systems, in the puzzling properties of the Higgs boson, even in the structure of empty space itself. Each mystery points towards something beyond our current understanding, something hidden, something fundamental. And despite decades of effort, scientists still do not know what it is. Perhaps the most humbling realization is how little of the universe we actually understand. Every human civilization in history has believed, at one point or another, that it was close to understanding the world. The new discoveries expanded the horizon. The Earth was not the centre of the cosmos. The Sun was not the centre of the galaxy. The visible universe was not the entire universe. Atoms were not indivisible. Reality kept becoming larger, more complex, more surprising. There is no reason to think the process has ended. If anything, modern physics suggests it may be accelerating. Every major mystery we discussed points in the same direction, toward layers of reality that remain hidden from us, toward phenomena that current theories cannot fully explain, toward a deeper framework waiting to be discovered. And that is what makes this moment in science so fascinating. For the first time in history, humanity possesses machines capable of recreating conditions that existed fractions of a second after the Big Bang. We can study particles that existed before stars, planets, and galaxies formed. We can probe nature at scales that previous generations could barely imagine. Yet even with all of that technology, all of that data, and all of that knowledge, we still find ourselves confronting enormous unknowns. There is something deeply humbling about that, but there is also something exciting, because mysteries are not signs of failure. They are signs that discovery remains possible. Every unanswered question represents an opportunity. Every anomaly represents a clue. Every unexpected result opens a door. The history of science shows that the biggest breakthroughs often arrive when researchers realize their assumptions are incomplete. And right now, physics may be approaching one of those moments. Whether the next breakthrough comes from CERN, a future collider, a dark matter experiment, or a theory nobody has imagined yet, one thing seems increasingly clear. The universe is not finished surprising us. In fact, we may still be standing near the beginning. The truly terrifying conclusion is not that reality contains hidden dangers. It's that after centuries of scientific progress, we may still understand only a tiny fraction of what reality actually is. And whatever lies beyond that fraction could change everything we think we know. Watch the next video